Alright, let's look at example 1310. We have a mass, it's a collar, and I think they call it a double collar because it's not only allowed to slide around the hoop, but it's allowed to slide, get a different color, in this direction also. So basically it's free to move as this arm rotates. This arm AB rotates about this point with a theta dot of a constant 3 radians per second. Alright, it wants us to find the force the arm exerts on the collar at the instant shown, which is 45 degrees measured from the positive x-axis right here. Alright. First, the force applied is going to be perpendicular to the lever arm, and that's just something that we kind of have to wrap our head around and acknowledge for future. The reason behind this is kind of like a lever. Think about if you had a lever picking something up, it's going to push on its maximum force perpendicular to that lever arm. So that's the best way I can explain it. Okay, let's start with the free body diagram. I'm going to make a coordinate system in what we'll call the unit R direction. So this is R. The transverse direction would be perpendicular to the arm that is sweeping, so it would be like this, the theta. And we can put in a perpendicular because in this case we are going to have a normal force, and it's going to be pointed directly down, and that's strictly because of the geometry. Alright. So let's take a look at this. We have a normal force, and it's pointing down on the collar from the hoop or the ring that it's going down. We'll call it a normal force, it's C. Okay, we also have our perpendicular force to the radial arm. Let's call that F. And if that's 45 degrees, that makes this 45 degrees. So when we break it up into components in the radial direction, we'll have a component of the normal force in this direction and a component of, well, the force applied is actually directly in the theta direction. So let's start summing forces. If I sum the forces in the radial direction, it's going to be equal to mass times the acceleration in the radial direction, and positive would be up away from our origin. Alright, we have a component of the normal force is going to be a negative NC cosine 45, or let's just put in theta. And that's going to be equal to the mass times the acceleration in the radial direction. Okay, let's call that equation number 1. If I sum the forces now in the transverse direction, and the positive transverse direction is going to be up and to the right. Or sorry, up and to the left. We have this force applied. It's going to be equal to the mass times the transverse acceleration. So we have a positive force applied, and then we have a component of the normal force acting in the negative direction, and it ends up being the sine of 45, or theta. Alright, that's going to equal the mass times the acceleration in the transverse direction. So we have two equations now. Now they did give us a radial function of theta that gives us the position of the collar at any instant. So I'm going to copy that back down. It is r is equal to 0.8 times the cosine of theta. Typically, if we see this, let's go ahead and take derivatives. Time derivative gives me r dot is equal to constant 0.8. The derivative of cosine is a negative sine of theta. And don't forget to multiply by theta dot. Taking the second time derivative will give me a negative 0.8, and then I would call this F and this G. I'm probably not going to do most of these for you anymore. The videos will end up getting pretty long now. 0.8 is a constant, open up a bracket, and then we have sine theta, theta double dot, plus cosine theta, theta dot squared. Alright, now, since we know these things, we can evaluate each at theta is equal to 45, theta is equal to 45, and theta is equal to 45. Alright, we get a numerical value because we're going to plug that into the radial component of acceleration that we learned was r double dot minus r theta dot squared, and the transverse component, which was r theta double dot plus 2r dot theta dot. So plugging these in, I get 0.566. I get a negative 1.697 and a negative 5.09. Alright, all we have to do, so notice we had theta dot given to us as 3 radians per second. If I take a time derivative of a constant, my theta dot becomes 0. So this term, we didn't need to know theta dot. So we were able to calculate r double dot just by knowing theta dot in this case. Typically, we would need a theta double dot if it had a theta double dot. We'd need to figure that out too. Plugging in r double dot minus r theta dot squared gives you a negative 10.18 meters per second squared, and this one also gives you a negative 10.18 meters per second squared. And why? Well, it all has to do with the geometry. They asked for at 45 degrees, that puts us right up here at the top of the circle. Our velocity is tangent to the path at that instant, moving directly to the left, so it's all because of the geometry. At any other instant it would be different. I bet we get those same magnitudes if we're down here. Alright, now we can use those to plug back into our Newton's second laws or our equations of motion, and you can get the normal force on the collar to be equal to 7.2 newtons. And interestingly, at this instant, the collar's not, or the rod AB is not providing a force, but only at this instant. Alright, thank you.